So if you are here today, probably it's because you know about BLOSK. BLOSK is a compressor, especially meant for compressing binary data. And BLOSK also has the capability to use many different codecs and filters in order to do this compression. So in order to assess which compressor or which filter it's fulfilling our needs the best, we created a new tool which is called Btune. And Btune has different modes of behavior. Today, I am going to introduce you to Btune genetic part of the things. So Btune, it's a way to find this optimal combination of compressions parameters. So, as I said, I am going to describe the genetic side of the things. Then we will have a glimpse on how the trained also works because it's using neural network models. So you can train Btune especially for your data sets and your needs. But let's start with the genetic tutorial first. So first of all, you will need to go to BLOSK genetic tutorial, okay? And just clone the repository.
Sorry to interrupt. We cannot see your screen.
Oh, okay. Okay, let me select its entire screen, share. Now? No?
Nope.
Okay.
It was working before when we tested it.
Yes. Okay, let me. We tested just a tab in Chrome, but I would like to. So let me share.
There you go.
Oh, okay. So, and now you are seeing the other tab, this genetic tutorial thing. Hello?
We can see now, yes.
Oh, okay. Good. So this is the URL for the repository. So I will leave 5 minutes for everybody to just to clone it and to install the required software. I am suggesting you to use Conda, like creating an environment on Conda with Python 3.10 or 3.11, for example, and you can do that easily with this command here. Let me. I'm going to stop sharing a little bit, and I think I will share the GitHub tab. Let me try again with the entire screen because I think it's going to be more useful. Can you see my screen now? Anyone? No, it's not working for some reason.
No.
Okay, let me go back again and share the tab. With the tab, yeah.
We can
the
see
problem
that.
is that I need to switch from time to time in order to see the chat, but no problem. Finally, you will need to install the Btune plugin, like as this. So hopefully you can install that. I will give you a minute for completing that, and then let's start. Okay. So I suppose everyone is set up and it can follow what we will be doing right now. So yeah, for the genetic tuning, it's best to use this diagram that shows the Btune is a state machine, what is called a state machine. So essentially what is a state machine is that it has several states, and then when you run it against a data set, Btune is going to check different codecs, as you can see here, that are tried sequentially, right? And whenever it tries a new codec, combination of codec or filter or any new parameter, it's going to take note of the different scores that is given, like a speed and compression ratio, and then it selects the winner based on your needs, what we call a thread. It's called. Yeah, well, it depends on a parameter, okay, that you can say. So this is how it works, and so in order to start things, let me show you how the benchmarks that the program that we are going to use is not very long. So essentially, what we are doing here is importing NumPy, BLOS2, and BLOS2 Btune. And in this case, we are setting this environment variable automatically in a programmatic way. And you can, instead of using, for those of you that are on Windows and you are not going to use a bash, because I will be using a bash during the tutorial, you can use, you can uncomment this, okay, and set this trade-off, for example, as you want. So, for example, trade-off in this case means that if we set a trade-off of 0, that means that we want Btune to favor speed. And if we put a trade-off of 1, that means Btune is going to favor compression ratio, right? Only will take compression ratio into account. Whereas we have a value between 0 and 1, it will do a different trade-offs. So values near to 0 means that we are making speed more important, and values near to 1 means that we are going to make compression ratio more important. Then you can also, during the tutorial, you can also have a look at the Btune parameters here, and you can uncomment. These are the defaults, and in case you want to override the defaults, just uncomment one of these lines, and it automatically will set these parameters, okay? For the time being, we are not going to uncomment anything like this. In this, I forgot to mention Btune trace. Btune trace is for giving a glimpse on what Btune is doing. And we set that to 1, for example. Then there are some compression parameters. Initially, these compression parameters will be empty. That means that Btune will choose an initial set decided by them. Although we can start using compression parameters, starting using compression parameters that you specify. Okay. Then, by default, we will compress data into memory. Okay, but you can also store the data in a file in case you want to see the size or whatever. Then we see how we create the array, the array, which is the array of the data that is going to be compressed. In this case, we are using random integers with a limit in the range in order to make compression work. Okay, because compressing highly random data it's completely impossible. But if you set a range which is far below the range of integers 64, then you can get some nice compression ratios. Then this is the way to do the compression. Okay. Specify we are creating this. This is A is a NumPy array, and then in order to create an ND array in BLOS2 is just using as array here. And then after that, we note the time that it takes, and we show some information. And for the compression, we just this B, okay, is a compressed array in memory. And for the compressing it, is just using the slicing operator, and we retrieve C is already a NumPy array. It's again a NumPy array. And we just display the time it took for the compressing it. And then we also take time for how long it takes to sum the NumPy array here. And then we also do compression chunk by chunk. So instead of decompressing everything in one go, we use the iter chunks method in order to decompress chunk by chunk. Okay. So this is doing that, and then this is another variation of the above, which is iterating over all the chunks in the BLOS container, and we do the sum for every chunk. Okay, and of course at the end the sum for doing the sum in NumPy and doing the sum with this partial summation of the compressed chunks should be the same, right? And we are using assert almost equal in order to do that. Okay, everything is clear so far? Any questions on how that works? Okay. Okay, so now, meanwhile, I hope you've been able to do some progress on the tutorial. So let me restart where we are now. Okay, so so we can continue by doing this command. And in this command, we are just going to execute the comp bench. Okay. And we activate the tracing. The trade-off is going to be 0.5, so in between speed and compression ratio. And the performance mode is going to be set to compression instead of the compression. So if we run this, we can see that we are creating the data, and then Btune is spitting out all the different measurements that is doing for every chunk. So every line that you see here, it's an estimation of the speed score here and the compression ratio here. And here you can see how Btune is changing the codec. Okay, it tests the codec with different filters. So zeros mean no filter, 1 means shuffle filter, and 2 means bit shuffle filter. Okay, so it's doing all possible combinations. And then another parameter is named split. That means that the blocks are being split in parts. That sometimes accelerates compression. And 0 means that the block is not going to be split. And this is the compression level. Typically is between 0 and 9. 0 is no compression, and 9 is maximum compression. Then the number of threads that BLOSK is using. In this case is 6 by default, because I am on a machine which has 6 cores. So by default, it uses all the physical cores in your machine. And this is the speed score, which is measured typically in gigabytes per second. So here is compressing at more than 1 gigabyte per second. And this is the compression ratio for this specific block. And this is the Btune state that I showed you before. We are in the codec filter state. And of course, the first time that it runs, it's always the winner, because we don't have history yet. And then whenever it finds in the next chunks, whenever it finds something or some combination that works better, okay, so it declares another winner here, for example. So here we can see that Btune has tested LZ4, BLOSK LZ, LZ4 again, and the compression is increasing here. And for example, for this combination, Btune has found that with filter 2, which is bit shuffle and no split, we have found a winner here. Okay. It typically it shows you whenever it compresses, it shows you the different things, the different measurements. But after the last winner, it didn't find any other winner. Okay, so for this case, it's LZ4 plus bit shuffle, who is doing a very good compression speed, which is more than 7 gigabytes per second, and almost 4.5 x compression of compression ratio. Okay, are you getting the same or similar results than me? Okay. Now, this is how it works, and at the end, you can see some different, some special measurements. So, for example, for creating for doing the compression, it took a little bit more than 1 second. The original size was 3 gigabytes for the array, and the compressed size was less than 1 gigabyte. And this is the compressed array in memory. All the different parameters here is the shape, the chunk shape, and the blocks, the block shape, the D type, which is integer 64, and the compression ratio. And here is the compression parameters. And also an interesting thing is that for doing the compression, compressing the array completely in memory took 2 seconds here. And the compression speed was 1.5 gigabytes per second. Whereas summing the NumPy array, it took 22 centiseconds. And the speed is a little bit higher. And then by doing compressing chunk by chunk, it took much less time than doing the compression in one go. So, and this is because when you are decompressing chunk by chunk, you are, I mean, the operating system or the hardware only needs to store the data in the chunk in caches, right? So the chunk typically is chosen so that it fits in caches. And that means that if the chunk is not going to be reused later on, the system doesn't even need to put it in memory. Okay, so avoiding this travel from the cache to memory is saving us time. So we are doing exactly the same decompression, but by decompressing chunk by chunk and not storing the result in memory, the whole result, we are saving lots of memory. We can go, in this case, we are going 6 times faster. And then another interesting thing is that if we decompress and sum chunk by chunk, we use 0.4 seconds, which is only twice of summing the NumPy array. Okay, which is not exactly the sum of the compressing and summing. Normally, is less than this sum. And it is less because normally the sum in NumPy needs to travel all the memory, all the 3 gigabytes, right? And that takes time. Whereas if we decompress chunk by chunk, the data is going to be in the cache, and the sum for NumPy is going to use that, okay, in the cache, and doesn't need the data to be transferred from memory into the cache. And this is why it is not the sum of this time and this time, typically. Okay. So are you getting similar results than me? In case you have some questions, just write them in the channel. Okay. So let's go with the next part. So the next part is about experimenting with different parameters in comp performance mode. Okay. So I would like you to do some experiments using these different parameters. So for example, for compression mode, so use a trade-off of 0.1. That means that you are telling Btune that you want to favor speed. 0.9, favoring more compression ratio. And these special values, so a trade-off of 1.0 means that we only want to look into compression ratio. Compression ratio is the only parameter that we're interested in optimizing, so making it large as possible. And when trade-off is 0.0, that means that we want Btune only to pay attention to speed. Compression ratio is not important. Okay. So I will give you probably 5 or 8 minutes to complete this exercise, and then we will proceed with some questions on this exercise. So remember, for those of you that are running on Windows, that you can uncomment this line, for example, and doing everything. Here is the performance mode, which by default is compression, but we are doing that already. But you don't need to deal with environment variables. Just uncomment and set different parameters here. The idea is that at the same time that you are doing the exercise, that you are exercising these values here, you need to take to pay attention to the questions. Okay, I think it's time. So let me ask you some questions. Which are the codecs and filters that win for trade-offs favoring compression speed, and the winners for compression ratio? Can you share them in the chat with your findings, please? So we can do a mini poll for that. In my case, for example, in my machine, I get LZ4 with bit shuffle and compression level 9. Yeah, Z standard is expected for getting high compression ratio, because the standard is meant to achieve very high compression ratios. At the at the cost of speed, of course. Normally, although the latest version of Z standard, they improve a lot, and it is quite fast. So in general, Z standard is a very good balanced compressor that achieves very high compression ratio, and it is also very fast. But when you want very fast speed, especially on old machines, LZ4 or Block Z typically are faster than Z standard. And for speed, which is the best codec that you? So when trade-off is 0.1, yes. So other people are saying that when we are setting a trade-off near to 0, that means that LZ4 is winning, which is usual, typically. Okay. And what happens at extreme values? I suppose that what you are seeing is that in one extreme it's LZ4, right? And in the other extreme typically will be Z standard. Is that correct? Good. Excellent. So one of the exercises, one of the questions is with the best guesses, what is the compression ratio and the compression speed achieved by the bench without Btune? And for that, typically you activate the changes in the comp bench around line 21 and run it again Btune. So let's do that. And in that case, sorry, it's not line 22 because I added, it's around line 42 more. So for example, here I am going to uncomment this, and because this is the best combination in my case. And filters, if you remember, shuffle is 1, is displayed as 1 in the logs of Btune, and bit shuffle is 2. Okay, so you can put whatever you want. In this case, I am going to keep shuffle, and in split mode, 1 means always a split, and 0 is never a split. Okay. But in my case, it's going to be always a split. So I'm going to save that and rerun without Btune. And running without Btune, it's just removing the Btune trade-off environment variable. So let's remove that and see what this is doing. Okay, so we haven't seen, we are not seeing now the lines for Btune. That means that Btune is not active anymore. And now the compression is the one that we just uncommented, the compression parameters. Okay, so in this case, we achieved a compression ratio of 4. It's pretty good. And for the compressing, we have seen that in this case, summing the NumPy array is 0.21 seconds, and the compressing chunk by chunk, it's half of this time. And curiously enough, the compression and summing the chunks one by one is less time than summing the NumPy array in the compressor state. This seems a bit counterintuitive, but the moment that you require less data to travel from memory into the caches for doing the sum, that means that you are consuming less time, right? So in this case, the time to decompress the data, it compensates, more than compensates the time that it takes to transfer the compressed data into the caches. And this is why we can see that in some instances, at least, the compressing and doing operations on compressed data can be faster than doing the compressions straight from uncompressed data. That depends on your machine, but typically you will see very close times between some in NumPy and the compressing here. And you've seen similar effect in your machines. Yeah, there's somebody who's playing that he's seeing the same effect. Okay, good. So with that, let's go to the exercise 2, where I am going to ask you to experiment with different parameters, but in the comp performance mode, okay, which is not the default. So you can do that by using this environment variable, or you can go here in the parameters and comment that. Let me show that to you. Here you say decomp, and you set performance mode here to decomp. And now so you see here that at the beginning, Btune is saying that performance mode is now in decomp, okay, because we set that programmatically in the script. And now Btune is going to pay more attention to the compression time, So the speed score will be evaluated for mainly for the compression time instead of for compression time. Here, for example, we have another winner, which is LZ4. Here we are using this is 2, which means sorry about that. Bit shuffle, okay, and this is compression level 8. Sorry, compression level 7, which is giving 10 gigabytes per second for the compressing. And the compression ratio is also pretty good as well. So the exercise is essentially the same than before, but I want you to explore the predictions for the compression speed instead of compression speed. I will give you a couple minutes more for exercise 2. And again, one of the new questions is what's the perceived difference in when performance mode is set to comp and decomp respectively. So for example, what I am going to do is to do a trade-off of 0.1. That means that I want to privilege or to favor decompression speed as much as possible. And let's see which is the winner for this case. In this case, the winner, it's this one, which is using shuffle, and then is doing a split and compression level 7, right? And then decompressing with 8 threads, because Btune also changes the number of threads. In this column here is the number of threads. So by using this, is getting the best performance. So let me activate that. So for example, here, we are going to, so compression level is 7. Shuffle, we already have shuffle. And then in the params, I'm going to say number of threads equals 8. And see how it works. Now I run without Btune. Okay, so interestingly here, the speed is worse than before, even though we said that we want to optimize for the compression speed, and this is quite usual. Typically, you don't get very reproducible results. Sometimes your machine is doing something else. In this case, for example, I am running this video conference setting with you, and things can be a little bit difficult to interpret. But I am repeating that. I am consistently getting this. So I don't know if the problem is that I activated the number of threads equals 8. Let me undo this. Yeah, it's more or less the same. Maybe compression level it's not very good at 7. Let's do a compression level of 3, which encourages speed. Okay, so this is better. So even though Btune sometimes reported that compression level 7 for LZ4 was the best parameter, you always need to put that to take that with a pinch of salt, because sometimes the time that it takes to compress some chunk, I mean, the measurements are not exact, right? So depending on many different factors happening in the machine, you can get better or worse performance. So be ready when you're using Btune. Be ready to interpret, to take your time, and to do different runs and get your own conclusions. Don't just take what Btune is saying blindly and accept that blindly. Just always do your own experiments. Okay. Now, okay, somebody is getting a segmentation fault. I don't know why. We are using an array which is a little bit large, so it's about more than 3 gigabytes. Maybe Jordan, you are using like a machine with small amount of memory, maybe. and that could be responsible for that. No, okay, yeah. Yeah, I mean, when doing a tutorial, you always have to do to achieve a balance between the amount of data that you want to show and to exercise and what the users have. I took as assumption that at least most of the people attending here will have 8 GB of RAM in their laptops. But if it is less than this, you can expect some random segmentation faults. That's normal. Maybe you can alleviate that by just reducing the size of the array, which is around here. So here is the size of the array. Okay, just you can reduce it 4 times by replacing this 4 by a 1. You can continue doing the exercises. This is going to take just 1 GB instead of 4. Okay. Good. So now it's time for experimenting with the balance mode. So balance is it's an interesting mode because it also takes in account not only the compression ratio, the compression speed and the compression speed separately, but both are used in order to assess a good compression parameters that makes a good balance between compression speed and the compression speed, and that also can provide better performance. For example, this is interesting when you want to optimize not only for compression speed or the compression speed, but for both, right? You want to, and in general, it is a good idea to use this performance mode, this balanced performance mode. So use 4 minutes for doing this example here. I'm going to do that also in parallel, so you can have a look. For that, I am going to use this parameter here. And then I'm going to comment this out. It is not important because when Btune is active, the specified compression params are not being used, right? But anyway, just to be more explicit, let's comment this, and then let's activate. Let's start with trade-off of 0.5, which are the most balanced situations. So let's see the parameters. Here we have a winner. Okay. It's LZ4 with bit shuffle and also doing a split. And this is the compression level 5. So yeah, let's give that a try. Let's uncomment this. And this is 5. And this is bit shuffle. And let's rerun this without Btune. Just remove that. Okay. So one thing that we can see is that the compression ratio is pretty good. It's around the maximum that we can get here. for LZ4, and the compression speed is also pretty good, 2 gigabytes per second. But the compression ratio, the compression speed is a little bit disappointing, right? So probably the prediction is not very good here. So let me try to optimize for speed instead of for compression ratio is not that important. So we have here a winner, which is using shuffle instead of bit shuffle and compression level 3. So let's try that and see how it works. Let's switch to shuffle on level 3. And let's run without Btune. So now the compression ratio is 4 instead of 4.5 that was before. But this is because the trade-off is more towards speed. And we can see also that the compression speed here is also pretty good, right? With this prediction. And also compression speed is also very nice. It's 4 gigabytes per second. So yeah, I think this is a good balance. And notice that I needed to rerun things twice, right, in order to get good results. This is a good measure. In general, Btune genetic is not about providing magical solutions. It's about providing a quick feedback to you on which are the best parameters, compression parameters that you can try. But the methodology is always the same. After running Btune, just take note of the possible candidates and then do your experiments manually without Btune in the loop, okay, in order to get the best results. Okay. Any questions so far? Yeah, so Nishan Man saying that it can run the benchmark again. Yeah, for some reasons, yeah, I don't know, when the trade-off is 0.1 or 0.9 happens. But my guess is that it's something related that your memory is scarce in your computer. I will give you a couple of minutes more in case you have questions, and then we'll proceed with the next section. Let me do a quick exercise on doing a trade-off of 1. That means that we only want the best compression ratio that I didn't explore myself during the tutorial. So in that case, here is a winner. And we can see that it's set a standard with shuffle and compression level 3, which is providing the best compression ratio here. Almost 4.8, which is pretty good. As I said, Z standard is really a very good compressor, which and also has exposes very nice speed. I have here an example with Z standard The prediction was level 3. And the filter was shuffle. And let's run without Btune this time. Okay, so the compression ratio, it's very good actually. The decompression speed is not stellar either, but it's not too bad. So yeah, in case you want to favor compression ratio, Z standard in general is the codec to go. Sometimes Z standard works better with shuffle, with bit shuffle as filters. It's Btune normally will tell you which one provides the best compression ratio as well. Everything is good? No questions so far? So Nishan is saying that he has 32 gigabytes of RAM. I mean, I am out of clues here because, yeah, I normally run Btune on Linux without any problem. I don't know. Maybe you are running some big programs or programs that are getting a lot of memory. I don't know. But for example, my Mac also has 32 gigabytes of RAM. Yeah, it's working well. And I checked also the tutorial with a laptop with 8 gigabytes of RAM, and it also works well. So yeah, it's interesting. Anyway. Okay, so if you don't have questions, let's go with the last part of the tutorial. So far, what we have seen is how to use we exercise the genetic mode in Btune. Also, Btune supports training models, deep learning models, in order to provide guesses on which are automatic guesses which are the best compression parameters, right? And for doing that, you need to train Btune, or to train Btune and to create models specifically meant for the data sets, right? So depending on the data distribution of the data sets, or depending on the trade-off that you are specifying, but mainly on the data pattern that the data sets have, the models are built. I am not going to show you how to build the models, because for training you need to get access to the Btune Studio, but at least you can use Btune for doing inference. So the BLOS development team provides a service that when you do a donation to the project, you can send us data sets for doing the training, and we produce the models for you, and you can run the models on your premises. So in this case, in order to, so I added some models here for the data sets that we are compressing. These are in the directory models. As you can see, there are 4 files, 2 files for for compressing and 2 files for doing the compression. Okay, and this is using TensorFlow behind the scenes in order to do the inference. So this has been pre-trained already in this machine, and I mean these models they are machine independent, right? So you can use in any platform that you will like. So in order to use inference, the interesting thing here is to provide these Btune's models, the environment variable, okay? Which is, you are saying that the models are in some directory. In this case, it's the model directory. So let's copy that. And let's see which is in this case, the trade-off is again 0.5, so a balance between speed and compression ratio. This Btune use inference -1 means that we always want to use inference because there is also a mixed mode where you can use inference at the beginning of the process. For example, if you specify use inference equals 10, so the first 10 chunks, they are going to use inference. And after that, the genetic algorithms takes over. So using the best guess for the inference, this tweaking or the genetic algorithm can still fine-tune over the predictions. Okay, but in this case, we are saying Btune to use always inference, and here it's the compression. The performance mode is compression here, and again Btune trace to see what's going on. So let's see what's happened. Okay. So here, as you can see, now we have this trace. That means that it loaded the model. It took around 1 millisecond to load the neural network model, and we can see here that the inference is predicting all these parameters, right? And with this prediction, Btune does these measurements for the score and for the compression ratio. Okay. In this case, it also says if it is a winner or not, but in general, this doesn't matter too much because we are in fully inference mode here, right? So every chunk is always predicted, is always predicted. And typically, it's always predicting Bloss-Scale Z here with shuffle filter, which is 1, and with a splitting, and compression level 5. So this is the prediction for that. So let's see if we activate that. Let's check if we use that. I think it was level 5, the prediction. And then shuffle and always split. And then if we rerun with these predictions, it is using now Bloss-Scale Z instead of LZ4. Compression ratio is 4, which is pretty good. But the compression speed again is not very good. But we are optimizing for compression as well, right? So let's do a rerun, and let's do a trade-off of 0, 1, and see which are the parameters. So we have a winner here. It's below scale Z. It's essentially the same parameters. Okay. But it is true that I did that on a Linux machine. It's a different one. So this is another thing. I mean, whenever you train Btune, it's important not only the pattern of the data, but also the machine that you're running, because of course speed depends very much on the platform. So let me rerun this on the, for example, in this in the Linux machine that I used in order to do the evaluation. And in this case, I am going to do the inference again. We can see that in this case, we are using 16 cores by default because this is a much powerful machine. And the last winner here, well, the prediction now is not block scale Z, or the prediction now is LZ4 with bit shuffle here. And if we use a trade-off of 0.5, in this case, instead of LZ4, the winner is block scale Z with compression level 5. So let's use that. I think it's compression level 3 that we had. And then let's run without Btune in the loop. Okay, and we see that yeah, we have a compression ratio which is pretty good for X, and now the decompression and sum is decompressing and summing chunk by chunk is approximately the same speed than summing in NumPy. Okay, with this big machine. If we enforce like or we balance, or we prefer to balance towards compression ratio, it's still compression ratio is the only thing that should be interesting. So it's predicting Z standard in combination with another filter 35, which is shuffling and doing delta encoding after shuffling. Okay. So, and with that, you can reach compression speeds of 22 gigabytes per second. Remember that this is a big machine. Okay. So, yeah, as I said, depending on your data patterns and machines, you can expect Btune. When you train Btune, you should expect different models, different results depending on that. So typically, if you want to compress for or to train for improving a balance between compression ratio and speed, typically you also need to provide which is the typical machine that you are going to use. It's not the same to optimize for a server with a CPU with 16 cores, like in our example in Linux, that for a laptop which only has 4 cores, for example. It's very different. They have different cache sizes and different number of threads and many different. And the memory speed is also very different on these machines. So it's important to train on the typical platforms that you are going to use in production as well. Okay, in case you are interested more in Btune, here it's you can read more about it, the different layers or different modes, working modes, and also the licensing model, which are the donation fees in case you want to use Btune models or Btune Studio. And here it's described a practical example for the Gaia dataset, which is a telescope which is mapping more than 500 million of stars in the Milky Way. And some testimonials that people is happy about or how they are using Btune and BLOS2. And with that, I don't have much else to say. We have still 4 minutes to go. In case you have some questions, now it's time to talk. So Nishan has did some experiments. zlib in this case was the winner. Yes, I mean it. As I said, your platforms is very important when decided which codec is better, right? So different codecs has different properties. This is why sometimes you can get zlib or you can get Z standard or BLOS-LZ or LZ4. And this is the beauty of Btune. You don't need to have a wild guess. Btune is providing you with tools to assess which are the best compression codecs and filters for you. And as I said, don't trust tools a lot. The last word is your own experience. Tools are good. In this case, Btune is good for providing hints, right? But in the end, you want to experiment and to test which is the one that works best for you. Yes, exactly. That's a good conclusion. Don't take compression as a black magic. It's always a matter of experimenting, right? And Btune is here for helping you in finding this the best compression ratios or the best codecs and filters for your tasks.